The dynamics of a snowboard. A snowboarder is riding a snowboard and produces an external torque on the board to rotate 360 degrees. For our system analysis, we will choose to treat the snowboarder as a constant external torque input on the system, which is the snowboard. We neglect the snowboarder's mass and focus solely on the motion of the snowboard. The external torque is applied for 1.5 seconds, just before the snowboard leaves the ramp. At the lip of the ramp, the torque is removed and the snowboard rotates with constant angular velocity in the air. When the snowboard hits the ground, it has completed a full 360-degree revolution about the z-axis with respect to the initial inertial frame. We chose to model the board as a cuboid with 1.6 meters length, 0.30 meters width, and 0.02 meters depth. The board will have a mass of 4 kilograms. The body fixed frame of reference has the x-axis coming out the front of the board, the y-axis coming out the left side, and the z-axis coming out the top of the board. This is our resulting inertial matrix.
In this system, we had two frames of reference, a body fixed frame that is connected to the board and an inertial frame that is located at the initial position of the system before any torque is applied. These were the equations of motion we used to describe both the translational and rotational motion of the snowboard.
Phase 1. Generation of angular velocity, non-zero torque. A torque was applied in the positive z direction with a magnitude of 0.8 Newton meters for a period of 1.5 seconds. The initial conditions before the torque was applied were that all the Euler angles were zero, the angular velocity in every direction was zero, and for the quaternion, the epsilon components were zero and eta was equal to 1. Phase 2. Coasting phase. Constant angular velocity and zero torque. After the constant torque is removed at the lip of the jump, the board coasts in the air until it has completed a full 360-degree rotation before landing in the same direction as the x-axis of the inertial frame. During this phase, we assume no external forces are acting upon the system, and that is a constant angular velocity and translational x-velocity.
Looking at the Euler angles and angular velocity versus time plots, we can see the only angle that changes with time is psi, and the only component of angular velocity that changes is the z component. The curved portion of the Euler angles plot from 0 to 1.5 seconds indicates a non-zero angular acceleration is present during the first phase. From the linear relationship of angular velocity with respect to time, we can conclude the angular acceleration is constant. During phase 2, after 1.5 seconds, the Euler angles increase linearly with respect to time and the angular velocity remains constant, which indicates zero angular acceleration. The angular displacement covered in the first phase is 58.38 degrees, and the remaining 301.62 degrees is completed in the second phase. The quaternion plots display the components of the quaternion vector versus time, and we can see the norm of the vector equals 1 at any given time, which should always be the case. In the position plot, x position increases linearly with respect to time, which is expected since we have constant velocity in the x direction. Here's the schematic block diagram. When the switch is turned on, a constant torque of 0.8 Newton meters is applied to the system. When it's turned off, zero torque is applied. The input is torque and the outputs are psi, omega z, and x. We could add a feedback loop in the system in the form of the snowboarder's eyes, which are the sensors that measure the outputs of the system, and their brain, which controls whether or not the switch turns on or off. The switch will be turned on at 4.5 meters before the lip of the jump and turned off if the distance is equal to or greater than 4.5 meters.